Welcome, calculus students. We're going to be talking about topic 512 today. So this is the last topic in Unit 5. And we're going to be, if you can't tell from this picture, we're going to be talking about implicit functions. So far we've analyzed functions. Everything we've done has been functions, implicit equations, Everything we've analyzed is function. We can identify critical values in the first derivative and evaluate functions to get the corresponding output. So we can tell if it's a max or a min. We can decide what concave up using the second derivative, all that good stuff. But now, what do we do when we have something that's not a function? Do these things still work? They want to be solved too. So right here we have the graph of x squared divided by 4 minus y squared divided by 1 equals 1. This is a hyperbola. So if you don't recognize it, that's a hyperbola. And so I know conic sections would have been in math 3 for you guys. Parts of math 2, parts of math 3. I'm not sure if they do all of it. It used to be all math accelerated, but it's been a while since I've taught that course all the way through. No, by the end of the year. Where does this graph have vertical tangents and where does it have horizontal tangents? Let's go ahead and try to answer that question. So vertical tangents, I can see one right here. And I can see another one right there. Those are the vertical tangents. And so that's at x equals -2 and x equals 2, which are the vertical tangents. And does it have horizontal tangents? And I'm going to say no. And what does that mean? So when we talk about vertical tangents and horizontal tangents, we're looking at a function. Vertical tangents are where the function is undefined, and horizontal tangents are where the function is, the slope is equal to 0. I mean, the slope is undefined and the slope is equal to 0. So let's go ahead and write the word slope. Slope is that's your vertical tangents. I'm going to go ahead and write BT for vertical tangents. And then slope is equal to 0. That's our horizontal tangents, which we'll use the blue so we can have color that helps us. Horizontal tangents. So, and we can see that on this picture that clearly the slope's not equal to 0 anywhere. We've got positive slope, a negative slope, a negative slope, and a positive slope. We'll get to that in a minute. And we have these two vertical tangents. And there are no horizontal tangents. Okay. Which quadrant is the, so it says quadrants. So what are we talking about? I'm just going to move this up. So quadrants being, this is Q1, Q2, Q3, and Q4. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. And where is the quadrant? In which quadrants is the graph increasing? The curve is increasing, meaning getting larger. It's right here in quadrant 1, excuse me. And quadrant 3. Basically, we're just paying attention to the slope is going up. Slope going up. So Q2 and Q3 decreasing. Decreasing. Q2 and Q4. And so when we look at that, we're looking at the slope again. So it's increasing. Slope is greater than 0, or the slope is greater than 0, and decreasing, slope is less than 0. Right? So we've got a positive slope and a negative slope. I'll maybe write that down. Negative. Okay. Find dy dx using implicit differentiation. So we're going to go ahead and take the derivative. So we've got 1/4, 2 times x to the second power times the derivative of x dx minus 2y times the derivative of y, dy dx, equals the derivative of 1, which is 0. And so I have 1/4 of 2, which is 1/2, x times dy dx, dx dx, which is 1, minus 2y dy dx. And so we get equals 0. 1/2 x equals 2y dy dx. And dy dx equals 1x over 4y. When I divide by 2, the 2 times 2 becomes 4. So there's our derivative. And the question is, does this support my answers I just got? So what we know about the first derivative, and we wrote the words down with slope instead of the first derivative, sorry about the squibbling, is that true? Does it support our answers? Can we still use the techniques we've already learned, but now apply them to implicit differentiation? That's really the question. Or do I have to learn something brand new? So let's see. For question 1, vertical tangents, so the slope needs to be undefined. And so if we were to check -2, 0 as a point and plug it in, -2, 0, we get -2 over 0, which is undefined. So dy dx evaluated at -2, 0 is undefined, which is what we found for our horizontal tangent lines, vertical tangent lines, excuse me. Slope is undefined, and the same is true at the other. Dy dx at 2, 0 is also undefined. Where is this equal to 0? Because the slope is 0, there's supposed to be a horizontal tangent line, and this is equal to 0 whenever x is 0. It doesn't matter what y is. When x is equal to 0, but x is never equal to 0 in my original equation. See how there's no x values, there's nothing on the y-axis, no y-intercept, so x is not ever 0. So it should be slope is 0, or actually dy dx equals 0 when x equals 0. Then my numerator will be 0. Doesn't matter what y is as long as y is not 0 at the same time, right? And that does not happen in the whole, because it's not on the original. But x is not equal to 0 in original graph, or it doesn't satisfy the original curve. I'm going to say original equation. Okay, and then question 2, when is it increasing, the slope is supposed to be positive. Is the slope positive in here? So that means if I plug in x bigger than 2 and y positive number, am I going to get a positive? And yes, I am. Because when they're both positive together, in Q1, x and y are both positive. In Q3, that's also true. They're both negative, which would make a negative divided by a negative, which is a positive. So when the signs are the same, it's going to be a positive. dy dx is going to be greater than 0. And then in Qs 2 and 4, when the signs are different, quadrant 2 and quadrant 4, and that's the same idea. So in the other two quadrants, so signs of x and y are different, and so then dy dx is negative, okay? When is the curve concave down and when is the curve concave up? So, I can't remember something. Okay, so the curve is concave up. If I look at this picture, the curve is concave up, as in holding water. See how it's both at the same time, if you will. Like if you only paid attention to this branch, which is the proper name for our parabola, it's doing both because it's sideways. And so, but it's concave up in quadrants 2, 3, and 4. Let's set it concave down first, though. Let's choose red. Q1 and Q2. Concave down, up, in Q3 and Q4. This is when y, the y value is positive. And this is when the y value is negative. Okay. It can be shown that the second derivative equals this crazy, crazy, crazy fraction. That's cool. Explain how this notices this. Explain how that helps me there. So this is, wow, something is missing. So let's really quickly check what that is. Just a y. Awesome. Some issues with that. So that's y cubed. Explain how this supports my noticing x had nothing to do with my concavity. The first thing I noticed is x had nothing to do with it. And so it's nice that x is not here anymore. Right? Show how this equation supports my noticings. So I know that it's supposed to be concave down when concave down when the second derivative is negative. And so the second derivative is negative since the numerator is negative. Okay. And the denominator is positive. So it's concave down when y is positive. Okay. Because y cubed is going to retain the sign of y. Okay. And this occurs and then it's concave up when the second derivative is positive. And since again we have a negative divided by whatever the sign of this is, and the sign, this is the same sign as y, this is the same thing. This occurs when y is negative. Okay. There we go. Questions so far? All right, so now we need to get our box full of wonderful information. And this time I tried to do a little different, something a little different. Let's see. Take it for what it's worth. I wrote it down. So what I would do right now is pause your screen, take a minute and write this down. All right, so implicit differentiation can be used to find the first and second derivative of any equation. Because remember, functions are relations as well. So critical points are the x and y values where dy dx equals 0 because they're critical points, and so it should be x comma y. We just kind of went with critical points when x is, and then we would find out the y value. But this time we need them both. So when the first derivative is 0 or is undefined, make sure that the points you find satisfy the original equation. So like we were able to figure out when y was undefined, but when the first derivative was undefined using our first derivative on our example, But when the first derivative was equal to 0, that was not on our curve, and it wasn't one of our horizontal tangents. Okay, make sure they satisfy. A curve is increasing when the first derivative is positive and decreasing when the first derivative is negative. First derivative is positive, it's increasing, decreasing, that's the same. This is not new. It's exactly the same relationship. The difference is you need to specify both x and y. A curve, that's why we talked about quadrants, because we're specifying both x and y. A curve is concave up when the second derivative is positive, and concave down when the second derivative is negative. Same thing. That's not new. Not new at all. But the new part, specify the x and y values. So what's nice about implicit differentiation is the rules have not changed. Please understand the rules rarely change in math class. They just don't. But the ideas that we can use, we get to keep using. All right, we'll be back for Check Your Understanding. Have a great day.